My name is Yuandong Tian. I'm a research scientist director in Meta AI Fair. Today I'm going to talk about our recent work on the LLM, reasoning and planning domain, and also agent domain. So the title is towards a unified framework of neural and symbolic decision making. Okay, so we all know that language model is being used very extensively in many different scenarios. So here I'm basically list a few possible applications that large model has already proven to be super useful, right? So people have been using large models for conversational AIs to generate content, right? And also use that to play against each other to basically do role play and also do AI agent as well. And recently, large model has also been used for reasoning and planning. And we also see that by using, for example, chain of thoughts, the reasoning capability of large model actually become much better. And at the same time, we also see issues with large models when we are trying to leverage that in different planning tasks. So in this lecture, I'm going to be focused on the reasoning and planning component. Since in Meta, I have been working with a bunch of very creative and very talented people together working on large model with reasoning and planning and try to find a way to make their planning and reasoning technique and strengths become much stronger to the next level. So let's see what are the interesting components that we can do for reading and planning. So one thing that we're going to think about is that in order to improve the existing reading and planning capabilities, of course, we want to understand what is weakness and how can we overcome? How can we overcome such weakness with different approaches? Here's one example that I probably use it for many different scenarios for showing that the large model really does not plan very well in different scenarios, especially in scenarios that is common in our daily life, right? So one example is the travel planning problems, right? So for travel planning, the task is super simple, right? We just ask the language model about a travel plan, right? So I want to say, I want to go to Hawaii, I want to go to Seattle, I want to go to California at some specific date with some specific budget. And then I want the LLM to give me a very clear, executable, feasible, and even optimal itinerary. So this is the task we want to go, right? So, and in order to achieve this task, then people may still start to think about some agentic behaviors, right? So of course, we first want language model to query a few informations, a lot of information from outside, from external world, right? So for example, you can ask language model to do a search, right? So, and it will give you some of the possible directions, the possible destination you want to go, right? You also want to ask language model to do a flight search or the hotel search, and you get multiple entries of possible hotels, as well as basically and also the flight informations as well. So once you have all this information putting together, then of course you want a language model to plan, right? So given all this information, hopefully the model can figure out a path, an itinerary that will connect all the existing information together into a clear path or itinerary that it can be executed. Right, so the figure to the bottom right, basically the figure that basically the real plan that we want to use in order to execute the plan. Right. Okay, so but interestingly, what happened is that if you actually use the current language model to do this planning task, it's actually not doing very well. So this is a paper that we published in this year's ICML as a spotlight. And in this paper, this is the main table that we put to show the incapability of language models for solving this kind of problems. Right. So first of all, the top chunk of the table basically shows that even with the GPT-4 Turbo, which is the model that is the strongest at that time, we actually see that the final pass rate of the entire travel itinerary is only 0.6%. So here you have percentage here, whether we don't show in the top. Right. So, but even if we give the language model the ground truth information of the tools then we ask the model to directly plan the travel, then the final pass rate is also only like 4.4%. So the pass rate definition is very simple, right? Given the kind of the itinerary, you really want to see whether every stage of the travel satisfy the constraints. Basically, the constraint means that you might have a criteria that you don't want to be in a smoking room, right? So you might want to say, I have a budget constraint that the budget cannot exceed some fixed amount of numbers, etc. So you can basically have some code to check whether the travel itinerary really pass all these criteria. But unfortunately, the final plan quality is not great. And you have to really have human involved in order to find a plan that is really executable. Of course, I mean, people will say, okay, this is like a paper that only that is a basic paper that is being published early this year, right? So, and like in larger model era, every month counts, every week counts, right? So, the paper published like half a year ago basically means like it's like an ages old, and people maybe don't care anymore. Right, so how about like using O1s, right? O1 is like the current state-of-the-art models for the reasoning and planning. And thanks for the courtesy of the first author for this paper, we also get some O1 numbers with this short planning benchmark. Then what happened here is that you still see that the overall pass rate is not great for O1 mini and also O1 preview. They are even worse than the model that is fine-tuned to that particular task. So it's not really solving you the problem for the short planning problems. And you can actually see the same thing for the LLM plan and for in other scenarios, right? So you can see that. So the figure to the left is actually from the DeepMind Gemini team, right? So in that paper, what they show here is that for planning problems like trip planning and also meeting planning, you see that the performance actually drops substantially with more complexity in terms of the number of variables and also the scale of the problem for the planning task, right? So while like Gemini is doing like great in these benchmarks, you will see like this worrying trend all the way down to 0, where you have more and more cities or more and more people showing that the problem scale goes up, right? Okay, so the figure to the left basically shows the performance before O1 release, but the figure to the right actually shows what happened after O1 release. Of course, you see that O1 is actually doing a very great job, right? So you see super high performance when this got applied to kind of smaller scale problems, like big gap between O1 and also existing models. However, if the scale of the planning problem goes up, right? So the plan length going from 2 all the way to like 14 or 16, then all of a sudden you see that the curve also drops to 0, right? So this is actually from OSU. The paper is called AM Cannot Plan. There's a study on that. So this actually basically gives you this kind of sense that while you can see the bias term of the curve is moving up substantially, the trend of the entire curve still goes down substantially, and the trend does not change over time, right? So this is actually, in some sense, a very worrisome kind of curve that even the best models that we have encountered have not solved this kind of problems. Of course, like the next slide will be, what is the solution? What are solutions? So in this lecture, I'm going to talk about the 3 possible different categories of solutions, right? So, and they are listed there. So the solution 1, of course, is the scaling law, okay? And we'll say with more data, more compute, and larger models, and hopefully in one day, then we're going to see a better performance and going to eventually solve all these problems with all these bigger models, right? So of course, they are very expensive. And then this also involve like a lot of engineering challenges, but may not necessarily involve like a new kind of thinking and thoughts about this, how we solve these problems. That's definitely one path. I don't want to comment on like how good or bad of this path, but this is just one option. Something that you can think about. There's a second option that's called hybrid systems. in that option, what we can think about is that, okay, so we can see it's very clear that there's two complementary paths. If we use deep models, like foundation models, they are very good at understanding the natural language instructions, but they are not doing very well in doing like a very good planning tasks, right? So they will have like a bad solutions. The solution is not high quality, and etc. Right. So on the other hand, there's another word called the combinatorial solvers or symbolic solvers. So these solvers are basically can give you optimal solutions in many different scenarios, and will have guarantees, and often run super fast compared to neural networks, and do not require GPUs in many cases, right? So, and these are basically like a very good solvers for complicated planning problems. But at the same time, these solvers don't understand natural language. They don't understand the user's request. They don't understand the many flexible scenarios, right? So maybe we should combine them together into the same system. Then you're going to see that these two can be put together, and you can give you something that is stronger than both of the side, right? So on these options, there are like several different ways of combining them. So which I'm going to talk about in the following slides. And that's actually option 3, which is actually say that there's actually a way to understand the neural network and find that there's a symbolic representation that emerges automatically from the gradient descent optimization. So that's something that could be super interesting. And recently, this is something that we have found in our very recent research. But I'm going to talk about that later after the option 2. Okay, so let's start with this one. So there's a different ways of combining the models with solvers. And of course, the first one that we can do is the tool use. Right, so for this, we actually have a follow-up work for the trial planner about how can we leverage mixture integer linear programming and neural network larger models together in order to solve the travel planning problems, right? So here, instead of asking the large model to directly give you the optimal travel itineraries, which is very hard and even infeasible given the current problems of issues of large models, how about that? We can ask the large model to first convert the natural language input into a JSON file. So here's the JSON file. And given the JSON file, it gives you all the symbolic representation of the request for the for the user. And given this request, combined with the flight and hotel information, you can actually call a solver. Here we are using mixed integer linear programming solver. And that solver will give you some symbolic description of the optimal itinerary. And you can use that optimal itinerary, and you can convert that back to the actual sentences. And this will be used as the response of the agent, right? So you can do this instead of like doing a direct pass. You can take a detour through the symbolic solver, and that detour will give you some solution that is guaranteed to work better. So we actually built a demo on top of that, and our demo actually was just accepted in this EMNLP demo session, to be held in Miami. If people are interested and people are joining EMNLP, please go ahead and take a look. So this entire thing can be a demo because it's in real time, right? So here's like this is a breakdown of the speed, right? So we actually fine tune instruction translator, and that will take like 2 seconds, 2.5 seconds, to translate from natural language all the way to the JSON file. And then we also have an MILP solver, interlinear programming solver, that will basically solve the problem. And the solving is actually sufficient, very, very fast. It takes 0.5 seconds, 7 seconds to solve the problem. So that this will make the entire demo real time. And people can actually play with it. And we also have human evaluations. And basically like human subjects are asked about these questions. Whether this system is useful, whether it satisfies the request, whether they offer a good amount of value for the money, and whether this is efficient. And you can just see that most of the human subjects, they are in net positive on our system compared to the baselines. Okay, so that's actually quite interesting. Of course, the next step will be multi-round dialogue, right? So here in the previous systems, what we do here is that the agent basically take the single round dialogue, take the user request as one single round of the request, and send this request to the neural network, to the large models, and will convert to a JSON file. But in practice, people are not doing that, right? People always start with some rough idea about travels. I want to go to Hawaii. I have no idea what else, but I want to go to Hawaii. But then the agent will try to ask a little bit more about details. How much budget? Like, are you a people who really care about money, or are you people who care about experience? Right. So there's actually a lot of detailed questions you really want to figure out, and this is actually a natural scenarios for multi-round dialogues and discussions. So in order to achieve that, we actually train an agent that can basically like proactively ask questions to the agent, to the travelers, and traveler will answer these questions accordingly. And the agent is aiming to efficiently get all the informations with the minimum round of dialogue, and then convert them into JSON, compare this JSON with the ground truth JSON that's being created privately from the data generation process. Right. So, and how we achieve this agent is that we actually design our agent constitution in order to allow the agent to follow these instructions. Right. So the constitution that we develop is called APAC constitution. So it consists of four different components. Right. So first, you want agent to be super accurate, and the second, you want agent to be proactive. Means that you want agent to ask a question proactively to get answers. You don't want agent to ask random questions. That is not interesting. You also don't want agent to be very passive, right? So you want agent need to find what are the interesting questions you want to ask and then answer them. And we also want agent to be efficient, which means that agent don't want to waste time and efforts to evaluate questions, but most important questions. The agent also need to be adaptive to different types of the travelers. So we actually set like 50 different personas of the travelers. Each persona of the traveler will depict different behaviors, and this traveler will have private hidden spreadsheet of most critical information they really want to get it correct. Right. So, and then we want to compare whether the agent can actually get all this information in a short amount of time. And finally, we also want agent to be credible, which means that less hallucination, less inconsistency, etc. So we can use all these constitutions and we can fine-tune the models. And we can see that after several rounds of fine-tuning using DPO, our models actually become a little bit more efficient in basically like two categories. One is called overall. Overall means like all the entries. And critical means that the critical entries for particular persona of the travelers out of like 50 personas. Then we also want to optimize the agentic scores involving practice clarification, etc. And we see that after a few rounds of DPOs, the performance actually goes up, and the system also doing a good job here. Right, so it's interesting showing that if you use like agent constitution, it's possible that we can improve the agent performance along different axes simultaneously with very simple techniques. And this can be also better than existing approaches. Like if you just use Llama 3.1b, 18 billion models, the performance is actually not great because it's not being fine-tuned along these directions. So recently, there's a separate paper that is also like involved like multiple like meta authors. Is that alternatively, we might also use agent as a judge instead of having humans as a judge, right? So in this paper, what we do here is that traditionally, we basically use large model as a judge to judge the behavioral agent. And we may only check like the final results of agent given all the outcomes. But in this paper, we're trying to use agent as a judge, and the agent we're trying to check like every steps of the target agent and to see like whether they are doing very well or not. And doing that, we were able to give you more refined and more rich feedbacks for the main agent to improve. Okay. Okay. So we are finishing this first part of using deep models to call the solvers in order to finish the task. So let's proceed with the second part, right? So the second part is that maybe there's a different ways of combining deep models with solvers. The second part is like, how about we use the solver to provide data to deep models to train better? For this one, we actually have a bunch of direction tasks, a bunch of research directions that actually are showing this is also a very interesting and nice trend to follow, right? So for this, we're going to introduce this Searchformer results. And for Searchformer, what we do here is that the goal is to basically predict the outcome of the planning task, right? So here it's a very simple planning task. You have a maze, you have multiple walls, and you want to find what is the shortest path between the starting point and the goal point. Okay. So here the maze is 3 by 3, and the shortest path is very simple, right? You just go all the way down and to the right, and to the left, and then you go to destination. Very simple. Right. So, but if before you actually get to the destination, get to the optimal plan, if you execute a symbolic solver, here the symbolic solver is A* search. Right. So A* search is a very seminar work that trying to use a heuristic function to find what is the optimal path from the beginning state all the way to the end state. It's being used very extensively in many different scenarios. And here we just use this approach to find the shortest path. So if you think about how A* search solve the problem, before it actually give you the final optimal plan, it also give you all the intermediate steps in order for you to reach the optimal plan, right? So for example, in this particular case, what happened is that A* search will start to create a new node doing the search and explore different part of the maze and to see which path can lead to the destination. So this entire procedure will create these intermediate steps, so which is shown in purple and also the teal colors. Right, so this basically is kind of internal steps of the search. After the search procedure was finished, then we actually find what is the optimal plan for the entire problems. Okay. So the idea of Searchformer is that instead of train a model that directly predict the plan, given the prompt is basically the description of a problem, this is something that people often do. Right? So we have some description of the problem, and then we directly predict what is the outcome, optimal plan of the problem. In our approach, what we do is that we start from an initial prompt. We can actually first predict the trace, the search trace of the problems. And then, given the search trace, we can predict the final output plan. So that's called the search augmented model. That's the model that we proposed in our paper as a first stage of models. So if you check like how many tokens we are using, right? So for these two settings, so of course, like the search solution only models typically will only generate maybe 100, 400 tokens, but the search augmented model may generate much longer tokens, number of tokens, because it will also output the trace, how you do the search, and then the plan. Okay. Then people may wonder, okay, now you have some kind of prediction problems that need to take a detour to the final destination. Do you think that's a good idea? The answer is yes. You can actually find that's a very nice scaling law curves that are associated with the search augmented models. So first, let's check out here the solution only curve. So this is basically the model that that can be used in many different cases, but also you see a scaling law curve is not so perfect. right? So for this curve, what happens is that you need to have like a million number of training sequences in order to reach something that is super high in terms of the performance on the test set, right? And this basically is using 175 million parameters in the solution-only models for a 30 by 30 maze navigation. Okay, not great. However, if you use search augmented models, and you check basically the curve, and you see that the curve is actually very different, right? So all of a sudden, what you see is that with a search augmented model of only 15 million parameters, 10x smaller than the solution-only models, you see training a curve that is much better than the original solution-only models, right? So with only like 50K samples, then what you see that the performance of the final score is already like around 80% compared to the 20% with the solution-only models, right? So when you have more and more training sequences, the performance is getting even better. Right? So now what you will see here is that this search augmented model become much more parameter efficient and much more data efficient. It gives you approximately the same performance with 10x fewer number of samples, 100K versus 1 million, and 10x fewer number of parameters, like 15 million versus 175 million, right? So with this simple trick, by adding this search trace, all of a sudden the performance actually getting much better. You can also do the same thing for the Sokoban game. So this is a game called Sokoban. The game is very simple, right? So you have one agent and you want to push the boxes to different destinations. And the only action you can take is to push the box forward. Right? So you cannot pull the box back from a corner or from a wall, and you have to basically start over from the beginning. Right? So then this problem basically requires a substantial planning because you cannot just do things randomly. If you push the box to the corner, then there's no way you can put a box back later. And this will basically conclude a failure stage of the game. You have to basically restart. And you basically see very clear also similar trends for the solution only versus the search augmented models. Okay, so now we can see like the scale law of the two kind of models are very different. Given that we first predict the search trace, and then we predict the final plan. Then people may wonder, how can we go beyond, right? So what we did is just the imitation learning. So we start from solver search trace, and then we use the search trace to train the transformer with teacher forcing to get the search augmented model. And this is already data efficient and also parameter efficient as well. But we can do further is that given the search augmented models, which is already end-to-end differentiable models, what we can do here is to fine-tune this model to achieve shorter trace, but still leads to optimal plan. Okay, so this is basically, in some sense, a very typical reinforcement learning task, and that is the Searchformer model that we end up with. So what we want to say is that we don't do really a reinforcement task, but what we do is very simple. We just do expert iteration. What it does is that once you have this search augmented model, you can actually sample this model many times with some diversity. And this sampling actually will lead to many different traces and many different plans. You pick the plan that is optimal, and then given all the optimal plans, check the associated search trace. And you want to find like which search trace is the shortest. You basically get all the shortest trace with optimal plan, and use these data, use subset of data as a training set for the next generation of the Searchformer. You can do this iteratively. Then what happens is that you still keep the same or even better optimality rate, but at the same time, the distribution of the sequence length per task now actually becomes shorter and shorter. Right, so you can see that at the beginning of the top of the figure, you see that the search augmented model and A star, they are sharing a similar distribution of the sequence length average per task, because the search augmented model is imitation learning results of the original A star search trace. So this is not surprising. But once you have done multiple steps of this bootstrapping, by iteratively by creating a lot of traces and their plans and picking the trace that is shortest, but still leads to optimal plan and put them back into the training set and retrain the model, or refine to the model, then you can see that over time, the distribution of the sequence length average per task actually shrink to the left, means that it's become shorter and shorter. That's why this paper is called the Beyond A star, which means that we are able to find shorter trace lengths while keeping the optimality of the final solutions. So, in terms of numbers, we actually also see improvements, right? So here we define a metric called ILR, which is the improved length ratio. That's the length ratio of the optimal of the A star search trace divided by the search trace that is discovered by the neural networks. So what you see here is that over time, the improved length ratio actually become higher and higher, which means that the final trace that is output by neural networks becomes shorter and shorter over time when we go through a step of bootstrapping. And then people may ask about like, okay, what happens if we check the optimality rate, right? It's possible that the trace for optimal results, optimal solution is shorter, but it's also possible that maybe the number of optimality also goes down. But actually, it's not the case. If you see the numbers, and you will see that the optimality actually goes up a little bit every time when you do the steps of iterations, which is something that's a kind of mystery, but it's still interesting to see. So after this number of steps iterations, you see the optimality rate goes up, and at the same time, the search trace is become much more efficient. And you see that this number of parameters, the performance is actually comparable when you use this Searchformer iteration procedure with 24 million parameters compared to the solution-only models that has like a lot large parameters, right? So 700 millions, and you can see that the optimality rates become comparable after this bootstrapping process. Yeah. So let's actually show that this is interesting steps, and our Searchformer performance, surprisingly, after this kind of bootstrap steps, actually doing very well. So recently, we also have a follow-up paper called a Dualformer. That paper is a V2 version of Searchformers. So what do we do here is very simple. So one of the weaknesses of the Searchformer is that the trace is often very long. It might basically takes like 1,000 tokens, or maybe 10,000 tokens before it actually give you the final outcome of the solutions. Then what should we do? So in the Dualformer paper, what we do here is that we're trying to reduce the length of the search trace by dropping randomly some portion of it, right? So we define different level of dropping. So we can say like maybe the close cost in A star search is not important, so we can get rid of them. Maybe the cost tokens in the create sentence, the create clause is not important, we drop them. We can also drop the entire create costs, right? So we have a different level of the dropping, and we also define the final level, the level 4 is basically drop the entire trace, and we just use the solution only data to train the models. Okay, so then what happens is that if you train the model with all different combinations of these levels of traces, then what happens is that the performance is actually getting better compared to the two cases that you train with only solutions and you train with a complete trace. That's very interesting. So we actually test this on maze of different sizes and also the Surco tasks that we used in the previous slides. And we actually see much better performance compared to these cases. And at the same time, the diversity of the outcome of the traces is also getting much higher. So diversity basically defined as how many clusters you see out of, for example, 64 number of rollouts that you have generated from the models. Diversity is important, especially for the test time compute, because if you have high diversity during the generation, then if you scale up your test time compute, then the performance will also getting much better, right? So in this paper, it looks like it's very simple. This simple approach, and it will automatically give you high diversity, because the input data is also very diverse. And more interestingly, there's a finding that is also very surprising, is that this approach, this final result called Dualformer, it will automatically switch between fast mode and slow mode by itself, depending on the problem specifications, and it will work better for dedicated modes in either situations. So we all know that usually people will talk about system 1 and system 2. So for system 1 settings, what happens is that the model will directly predict final solutions without any thinkings. And for system 2, usually the model will first think around, or what should we do? As there's some search process, and then come up with other final solutions. So usually for system 2, we think like there are two different discrete modes of operating, and we want two different models to deal with these two kind of thinkings separately. And we can basically try to control on top of that to ensure which one to use. But now with the Dualformer, we actually see this surprise behavior that once the model trained on this mixture of data, it will automatically switch between system 1 and system 2. So sometimes the Dualformer will output, for example, the create token. So once the Dualformer output the create token, which means that the model will start this kind of slow thinking process until it gives you the actual plan. Sometimes the model will give you a plan token at the beginning, which means that the model will directly give you the answer. That's actually quite interesting. So basically, you see that this kind of behavior automatically emerges from the training, and without basically having human giving like explicit evaluation, explicit like signals there. So here you see that for the Dualformer bracket auto, this means that this model is doing an auto mode. We are free to let the Dualformer output any kind of tokens. It may output a plan token, which is the system 1 settings, and it may also output a create token, which is system 2 settings. And in the same time, you see that the performance is getting better than if your model only trained on system 1 and the model only trained on system 2. And moreover, it's interesting to see that we can actually control how the Dualformer is operating by only control the first tokens, right? So if we say the Dualformer is forced to generate the first token called create, then Dualformer is forced to be entering the system 2 settings, which is slow settings. If the Dualformer is forced to create a token called plan, then it will basically give you a system 1 output. And interestingly, we compare this Dualformer fast, which means that the Dualformer is forced to operate in a fast mode, with the dedicated fast models that is notified by solution only. You see the performance is also getting better. If you compare the Dualformer, which is forced to be in the slow mode, and you can actually see that its performance is also better than the baselines that is trained on complete trace, which means that it is forced to, the model is dedicated to a slow mode. Right, so it's interesting that the model can switch to both modes, and at the same time, if the model is forced to use one mode, is also still better than the dedicated models trained on particular data. And we also tried this idea in math problems. So this problem is more realistic, right? So for math problems, what we do here is that, so we start from this math data set, which has a very long explanation about how we arrive at the answers. And then we can basically randomly decimate sentences from the channel of thoughts, and then for training models. And the resulting model is actually quite interesting. It gives you much shorter and concise steps. At the same time, it still give you a little bit better performance. So here's the examples, the performance that you get, right? So you see that in the previous work, people already discovered that by augmenting the chain of thoughts with existing language models, we created a set called augmass, which is our baseline. So this augmass already give you better performance compared to the original mass data set. But with our approach, with different ratio of dropping, we actually see even better performance. And at the same time, the trace length is also shorter. So in the end, we have this this kind of unfair comparisons between the Dualformer and also the O1, right? So you actually will see that the Dualformer will give you the correct path towards the destination with all the explored states that shown in the red. And the O1, without any training, does not really understand what's going on inside this main settings, and we only give you a pass that basically break all these situations, break all the walls. Right. So in this case, we show that after the training, this Dualformer is able to do good planning, and the planning is reasonable, and it's better than the O1 preview in this particular problems. But I would say this is not a fair comparison, because ideally there should be fine-tuned version of O1 preview on that particular data set and see how good performance is. Okay, so now I conclude the second part of the option 2. So let's go to the option, the last part of the option 2, how we can train the models and the solver at the same time in end-to-end manner. So for this one, we're talking a little bit about a little bit different settings. This setting is also using combinatorial solvers, but it's applied to kind of real-world problems that requires optimization. So think about like you want to optimize very complicated functions that are differentiable, but at the same time, it also need to subject to the combinatorial constraints, right? So you have some combinatorial constraints, and the objective is nonlinear. There are many different real-world domains that will actually cover fall into these categories, right? So for example, you want to optimize some computer systems, you want to optimize some antenna designs, optimize some devices in physics. So all these problems, usually you cannot write down the optimization problem in linear form. And this basically prevent you from directly calling a combinatorial solvers to solve the problems, right? So here's one example that we actually encounter in our productions. So this problem is like embedding table placement. So suppose like you have K tables, they are embedding tables, and they have n identical devices. Here devices means GPUs. And then you want to place these K tables to n identical devices such that each device will have a lot of tables, but does not exceed the memory capabilities, capacities. And the goal is to minimize the latency, which is estimated by a neural network. So if you want to formulate that problem in a mathematical way, you actually end up with these formulations, right? So here x is a binary variable representing that this table I is being placed to device j. Okay, so of course, like for each table I, we want this one to be placed to device j, some device j. So that's why you have some j, xij equals to 1. And the another constraint is that for all the device j, you want to basically you don't want the final memory consumption exceeding any memory budget. That's why you have this sigma I xij mi smaller than or equal to mj. Right. So you have these three constraints, and because each xij is binary, this makes this entire problem combinatorial, and at the same time, the loss function is nonlinear because of system issues. Right, so there's a batching communication, lots of different issues that will lead to highly nonlinear objective functions that is pretty hard and tricky to deal with. For example, if you use any kind of optimization technique, for example, genetic algorithms, to solve this problem, it may take forever to even find the feasible solutions. So then the question is that maybe we should still get like good optimization solutions. And at the same time, leveraging the existing combinatorial solvers. So then what we can do is to, instead of solving the original problem in the original space that is nonlinear, we can actually find a latent space such that the problem become a little bit linear in the latent space. So what we do here is that we first basically like try to learn a surrogate called C. And basically this surrogate called C is a function of the problem description Y. So Y is some description, say like maybe how many GPUs do you have? What are their memory capabilities, right? So these are basically the problem descriptions. So you first predict some surrogate cost, and then given the surrogate cost, you want to solve a linear problem, which is shown on the right. The linear problem will give you a solution x star, which is a function of y. We really want this linear problem, the final solution, to optimize the original nonlinear optimization problems as much as possible. So you have this kind of a loop. So how are you going to solve this problem? It's actually very simple. You can just like leverage gradient descent optimization. So here's basically the computational graph of the gradient descent optimizations. Right, so you first start from the problem description y, and that y first get into the c equals to cy, and this will basically give you a surrogate coefficient c, and that c will be plugged into a solver, and that solver will give you a solution. That solution will be plugged into objective, which gives you the loss function. So in order to find what is the best way to represent the surrogate coefficients, and what we can do is that we can do backpropagation. Right? So our goal is to find, okay, what is the best way to minimize your loss? And I don't care about all the intermediate stages, but I just want to find what is the best way to minimize the loss, subject so that the entire pipeline will be working. Right? In order to do that, you want to find what is the best way to specify the coefficient C. But what we can do is we can backpropagate all the way down, and you can actually find the optimal weights for that associate C equal to CY parameterizations. Okay. So we actually tried these ideas in this embedding table sharding, and it's actually doing quite well. So what we can see here is that, so here there's two tables, two figures. The left figure basically shows the solution quality, right? So you want the solution to be as low loss as possible. Ideally, you want them to be 0. That would be the best one. And on the right, you also want to care about the deployment runtime. You don't want the deployment to be too slow, so you also want to also reduce the deployment runtime. So in that case, we can actually leverage multiple variations of our approach. Right, so we have these 3 variations. One is called Surco 0, which will basically do the backpropagation on the test time, which is slow, of course, but it will give you good solutions. We also have the Surco prior, which is another variation that directly learn this C equals to CY mapping, and use that mapping to directly predict the C and call the solver once. Then you get a solution. You also have a hybrid version of it, which means that you first call the prior module to find the optimal, the initial value of C, and you continue optimizing the C over time. So then what we see here is that our 3 variations actually give you a very good trade-off between the solution loss and the deployment time. It's actually much better in solution loss compared to the existing approaches, right? So this includes domain heuristic, greedy, and also the dream shot. This is a kind of one approach that uses reinforcement learning to optimize these nonlinear optimization problems. On the other hand, in terms of deployment runtime, our 3 approaches is also doing quite well, especially for the Surco prior, because you only need to predict the coefficient C in once, and it's actually much faster. And at the same time, the performance is also reasonably good. We also apply the same idea to other design problems. So one industry design problem is called inverse photonic design. So for that problem, what we do here is that you have this kind of a very small from 80 by 80 grid. So this is shown on the top middle. So this grid is super small, it's in the nanometers. And the goal of this design is that once you send the lights from the top, you want the design to change the trace of the light so that it will land onto different part of the bottom, depend on their wavelengths. So the reason why this can be done is because once you put design in this very small nanometer scale plate, then we can actually the light will basically behave like waves, and the waves will interfere in the diffraction and diffract at different places, so that the light will go to different places at different frequencies, right? So the reason why we're not using any mirror to do that is because the place is so small that you cannot place all the mirrors there. You have to use diffraction and interference in order to make this happen. We guide the light to different routes. Then the optimization problem obviously is very complicated, right? So here's optimization loss functions you want to optimize. You have to first do a simulation given the current setup of the design. And given the simulation, you want to compute the frequency response, and then compute cutoff frequencies, and then compute all these equations to find the overall loss quantities. Okay, it's high nonlinear. But at the same time, the design space is combinatorial, because at every entry of this 80 by 80 grid, you can choose either to put 1 or put 0 into this grid. And this is a binary problem, of course. But also you have linear constraints, which means that you want to find a feasible solution. So the design has to be implemented by a brush, right? So when you manufacture the object, you have a brush to move these things around in order to carve all these designs onto a plate. So the size of the brush become a constraint. Now you don't want to have one single dot out of nowhere to be manufactured. This is not manufacturable. So this actually could give you a different constraint that can be written as a linear constraint. But then the entire problem actually become quite complicated. So there are several different benchmarks that people are thinking about, right? So you can try to bend the light from top all the way to the left by using these kind of very specific and nice line patterns. You can also basically like split the light into two different streams. It's called a beam splitter. You can also do other kind of works like the wavelength multiplier. So then we're actually using our approach. We are able to find good designs using this optimization technique. Basically, this curve basically show that our approach called a Surco 0 and Surco hybrid have a much smoother basically convergence curve compared to existing approaches, which called a pass-through. So this is also a gradient-based approach, but there's no neural network involved, and the curve looks very unstable, and it takes a long time to converge. Okay. Of course, there are some limitations of such approaches, right? So first of all, if the function f is not differentiable, what should we do? And also during the training, we actually need to call the solver every time, so which is slow. And you also require the solver is very programmable. For this tool, we actually have several follow-up work in order to achieve these problems. Due to time limitation, I won't be able to tell you the details. But if you are interested, please feel free to reach out. Feel free to read these papers, and the code is already online. Okay, so this concludes the second part, which is basically hybrid systems. The hybrid system that can use both a neural network, the larger models, and also the solvers. And in the last part of the lecture, I'm going to talk a little bit about option 3, whether deep models can actually converge to anything symbolic. So this is actually something that can be very interesting, because we all know that there's actually two different conflicting narrations in our daily debates in Twitter or in X, right? So there's one part of the people who actually say, oh, large model can do everything. When the parameter of the models become larger, what you see is you're going to see so many emergent behaviors with more and more parameters. So when you have more and more parameters, then we will enjoy all these capabilities without too much worry. Then we can just sit down and do our engineering work, and the model will do enrich your AGI later. That's one way of seeing the entire situations. But there's another different directions, different kind of opinions, right? So, and people actually also think about otherwise, because from many experiments, what people actually see is that maybe language model is not doing anything really intelligent, right? So maybe language model is basically just doing retrievals. The reason why it is doing reasonably well is because in training sets, you already see good examples, right? So recently in Apple actually have one paper called GSM-AK Symbolic. That paper actually give you this kind of examples that by adding irrelevant topics, irrelevant sentences into the GSM-AK dataset, all of a sudden you see a huge drop of all the models' performance on the dataset, right? So it's actually very surprising because the final answer is not supposed to be changed after these random sentences being inserted. But unfortunately, all these models will experience huge performance drop. Okay, then how can we actually address these problems, right? How can we understand better why and what kind of representation language model is used to do the reasoning and planning? That's one of the core problems that people may want to ponder on during the career and the studies. So in order to achieve that, so here I give you one example about how we should analyze and understand the representation that is learned by the natural language, by the training of the large models. Here's one simple case, which is called a modular addition. This is a very simple reading task. It's very simple, right? So you basically give A and B, you want to predict what is C. So basically predict the answer of addition. But the addition is modular, which means that there's a mode D here. So if the C is too big, it will wrap back to the smaller number of that is in between 0 and D minus 1. Okay. So for this task, people may wonder, it's very simple, right? So there's only D to the D square number of possible inputs. So this should be give you something that's super simple. Then maybe the network, after train this model, will have implicit tables to do retrievals. But actually, it's not. So what happened here is that people actually discover the learned representation of such a simple problem is a Fourier basis. So there's many papers that already show that large model, once you train on this addition task, they will actually show this very nice sine cosine curves as a representation for different numbers. The question is why? Oh, it's very simple why you can see that. So in order to explore what's happening in the very recent work that I did, we actually just use the two-layer networks to understand the behavior better. So we have two-layer networks, bottom layer and the top layer. And the bottom layer basically takes one hot representation of A and B. And they are basically be sent into the two weights matrices, and they add together, and then they send to Q different hidden nodes, each with quadratic activations. And then these activations will be sent to the top layer, and it will give you the one hot representation. As it will give you the output will be compared with the one hot representation of C. A very simple settings. And surprisingly, you actually also see a Fourier basis that is emerging from the training. So in order to understand what's going on, let's convert everything to Fourier domain, right? Obviously, we should do that. And then we'll make things much easier to analysis, to analyze. So you basically do the Fourier transform, and you get ZA, ZB, ZC. You have all these complex number coefficients. Because this original W, WC, they are real, so there are some additional conditions that need to hold, which are Hermitian conditions for the associated complex numbers, ZA, ZB, and ZC. Okay, so given all these settings, let's look at what the gradient descent solution look like. It's actually very regular, right? So here that the figure is two-dimensional, the x-axis is a hidden node index. So here you have very simple settings. You have d equals to 7 and q equals 20. So q is the number of hidden neurons, right? So these hidden neurons index from 0 all the way to 19. And for y-axis, that's the frequency of the Fourier transform, right? So what you see here is that for each frequency, there's actually a few hidden neurons that will show strong frequencies at that particular frequency k, a strong response of that frequency k. So if you check how many neurons are showing strong, strong like a response for that particular frequency, you can see that the number of number of neurons is having like a very interesting structures. So if you check for each frequency k, so for frequency k equals to 1, you see there's 1, 2, 3, 4, 5, 6, there are 6 neurons that show super high response of that particular frequency. For k equals 2, you also get 1, 2, 3, 4, 5, 6. Okay, you get all the 6 solutions. Of course, you also will see all the 4 solutions. So this is another example, right? So for k equals 2, you see 1, 2, 3, 4. That's 4 other solutions, but you also see some bias terms across the other neurons. And so far, you have seen all the 6 out of 4. Is there any other orders? Also, is interesting, no. If you check the more statistics on gradient descent solutions, right? So here the statistics on d equals 23. So the figure to the left shows all the training curves, right? So and the right shows like distribution of the orders at different frequencies. And you see very sharp peaks at 4 or 6, 4 and 6, right? So in these figures, very clear. And what happened to a larger setups? Now we have like 3 different settings, right? So d equals to 23, d equals to 71, d equals to 127, and also with different weight decays. So you see that most of cases you still see 2 peaks, order 6 and order 4. Unless that you have a very strong weight decay, in which like all the solutions collapse into order 0, which means that there's no solutions, or everything is 0. Right. So and other than that, you see like a strong peaks there. Okay, then why? So in this paper, what we see is that we actually come with we find a nice structure of the loss function solutions. That structure can be useful for explaining what's happening there. So first of all, you want to rewrite this MSC loss into this form. It has quite complicated terms. Right, it has 1 minus term and also 3 terms that are sum of squares. Okay, and this term is representing in this way. So you have the red one and the blue one. Oh, sorry, and the green one. And people might wonder, okay, why I want to write this MAC loss into such an ugly form? That does seem to be interesting. But interestingly, given these forms, we first can come up with a sufficient condition of the global optimization or global solutions. Right, obviously, if you set this RKK to 1 and all these sum of square terms to 0, you get global optimization, global solutions. But then the question is like, why and how to achieve that? The objective is highly nonlinear, right? However, in order to achieve that, you can actually leverage some very nice algebraic structure that's happening in the 2-layer network. First of all, we consider all the spaces of 2-layer networks, but with different number of hidden nodes. So this space is big Z. It actually have nice structures. The structure is called semi-ring structure. If you define a ring addition to be like a concatenation of 2 hidden neurons, and multiplication being a chronicle product along the hidden dimensions, then this entire structure becomes semi-ring. And what makes things interesting is that these 2 terms that is happening in the previous loss functions, they're actually the ring homomorphisms. So what is ring homomorphism? It's actually very simple. It basically, you want that basically this function is a ring homomorphism if that particular function respect the addition and multiplication across ring and normal addition and multiplication. Then they are ring homomorphisms. So what does that implication is that you actually will see you can start with partial solutions. So suppose Z1 is a partial solution that only satisfies one single term of your loss functions. And Z2 is another partial solution that only satisfies another single term of your loss solutions. Okay, they are partial solutions. They are not the entire solution. But interestingly, because of the ring structure, if you multiply these two together, then the resulting Z will satisfy both of the constraints at the same time. So what does that mean? What does that mean is that you can actually start with some partial solutions that are very partial. They only satisfy some part of their constraints, but you can gradually construct more and more complicated solutions with your multiplication and your addition. And then it will actually give you the global optimization, global solutions to your original loss functions, right? So the entire process does not require gradient descent. You just construct this algebraically, and then you will give you will get a solution that is global optimal to the original loss functions. So you can construct a solution this way. You construct a solution like order 6 by multiplying order 3 and order 2 solutions together and add over all the possible frequencies. You can also construct order 4 solutions. And you also construct solutions that correspond to the perfect memorization, which is actually order D solutions. So these construct solutions are nice, but people may wonder, okay, how is this related to the real world? This is, in some sense, a symbolic and abstract world created by mathematicians. And we have nothing to do with the real world. But actually, what happened here is that if you compare the gradient descent solutions with the solution that are constructed previously, we can actually see an exact match between the two. So first of all, in these particular settings, you can see many, basically all the frequent solutions, they are order 4 or 6, which is already shown in this histogram. And also, if you pick this order 6 and order 4 solutions, and you try to factorize them according to the previous defined ring multiplication, and you realize that 95% of the solution, they can be factorized into either 2 by 3 or 2 by 2, which is the same as the construction that we previously did in our experiments, in our theoretical construction. And their factorization error is small. And finally, if you check every entries of the factorization, what you see is that 98% of solutions actually can be factorizable into the constructed forms. They actually fall into the form that we constructed previously. So which means that the gradient descent solution matches very well with the construction from the theoretical side. That is quite interesting. And also, if you check distribution of the parameter in these solutions, you actually see very nice regular structures. Right? There's sharp peaks in different angles that correspond to the higher symmetries. Right? So this is something that's quite interesting that haven't been explored yet, but that can be nice follow-up papers to understand them better. So what are all these implications? So first of all, so it's very kind of surprising that neural networks, if you run gradient descent on top of that, it will give you a solution that is very simple, very similar to symbolic representation, right? So maybe in general, the neural network or maybe large models will also convert to some solution that is symbolic, but we don't know about. We haven't constructed that yet. But here we just give you an example that a reasoning task will give you a solution that is symbolic after the training with gradient descent, right? And second, it will give you a path, alternative path towards the solution other than gradient descent. Right? So you can think about gradient descent can give you a solution, but you can also have some advanced algebraic operation that is also give you the same kind of solutions. So maybe in the future, we don't need gradient descent anymore. We just need algebraic constructions to combine small solutions to the larger solutions. And then maybe gradient descent will become obsolete eventually. So that's why I want to introduce this part of work. So this might suggest a different path compared to the existing path that we have. Maybe in the future, instead of having people praying about the distributed system not working well, we can open the black box and have a principal approach to do this. Thanks for your attention.